Good morning, class. We are looking at chapter 3, derivatives. Here's section 3.5, the chain rule, the third part, related rates. We have covered derivatives and rates of change, the derivative as a function, basic differentiation formulas, the product and quotient rules, the chain rule, the first part, the second part, implicit differentiation, and now the third part, related rates. From composite function, we get the chain rule. So f of g, the derivative would be f prime of g of x times g prime of x. Or in Leibniz's notation, dy dt is dy du, du dt, or dy dx is dy du dx. In this section, related rates, t is the independent variable. So reminding you of the differentiation formula, starting with the definition. F prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. Then we have the derivative of x is 1. C times f of x, c can come out, and the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivative. We look at some basic differentiation formulas, such as the power rule. The derivative of x to the power n is nx to the power n minus 1. The derivative of exponential is itself. Trigonometric functions, such as the derivative of sine is cosine, and so on. Product and quotient rules. Composite function results in the chain rule. And the derivative of any exponential is itself. The derivative of e to the power of kx is itself times k by the chain rule. The derivative of e to the power of g of x is itself times g prime by the chain rule. And the derivative y is b to the power of f of x. The derivative is itself. Then ln b is by the logarithmic properties. F prime is by the chain rule. Therefore, when y is b to the power of f of x, y prime is itself b to the power of x times natural log of the base times f prime of x. And now related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing. And the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. So what's the procedure? Number one, find an equation that relates the two quantities. Number two, use the chain rule to differentiate both sides with respect to time, which means in the case of a related rates, independent variable is a t. Therefore, the derivative of x is dx dt, the derivative of y is dy dt, the derivative of z is dz dt, and that's important to pay attention to. And so the Leibniz's notation with respect to t, dy dt becomes dy du dt. Now this warm-up example is regarding what we just mentioned. Air is being pumped into a spherical balloon so that its volume increases at the rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we want to look at this as an application problem, as a word problem, what is given, what is missing. So we can discuss the given. The rate of increase of the volume of air is 100 cubic centimeters per second. We're going to look at what is missing. The rate of increase of the radius when the diameter is 50 centimeters. So that's sort of understanding the problem verbally. But we have to also do it, and more importantly, symbolically, mathematical symbol. So first and foremost, a sphere, what is the shape? And we want to relate the volume and the radius. So this is the shape looking like a basketball, and we should know the volume is 4/3 pi r cubed, and the relationship between diameter and the radius is d equals 2 times r. So we need this formula from algebra / geometry / trigonometry, you name it, previous knowledge, prior knowledge of mathematics. And now we're going to reread this and say, okay, how do we write this symbolically? The rate refers to the differentiation. So dV dt, the rate of increase of the volume, dV dt is 100 cubic centimeters per second. What is missing? The rate of increase of radius, dr dt. At what point? When d is 50, which makes r 25. We're going to write the volume is 4/3 pi r cubed. dV dt is 100 cubic centimeters. That's given per second. What is missing? Find dr dt when r is d over 2 or 50 over 2 or 25 centimeters. This explains everything symbolically, and it makes it easy to finish the job. So we want dV dt, everybody. We're going to go with the Leibniz's notation. So as we move from v to t, the intermediate variable is r. So dV dr dt. Now, to find dV dt, please understand that this is just a multiplier and it's a number. So dV dt is 4/3 pi. And now you're going to work on r cubed, which is 3r squared dr dt. And dV dt becomes 4 pi r squared dr dt. We want dr dt. We're going to divide both sides by 4 pi r squared. Dr dt becomes dV dt divided by 4 pi r squared. Replace dV dt with 100 or 100 cubic centimeters per second with the units. Divided by 4 pi r 25 squared. And bear in mind, if you want to put the units, for this one would be cubic centimeters per second, for this one would be centimeter squared. So you can see the result. Or ultimately, the units would be the units of the radius over the units of time. Everybody knows 4 times 25 is 100. Therefore, I can cross this and cross this and cross the exponent. And I get precisely 1/25 pi. In calculus, make sure you always write the exact answer. If they want you to answer it with decimals, then pay attention to how many, and you would write the radius of the balloon is increasing. Why increasing? Because this is positive. At what rate? 1/25 pi, roughly 0.0127 centimeters per second, units of the radius over units of time. Example 1, a small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at a rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So we are going to translate this symbolically. And to do so, first and foremost, we notice we are dealing with a circle, and we want to relate that to its radius. How? As far as the area is concerned. So let's write a bunch of information. Number 1, here's the shape of a circle. Number 2, from the center to the circle is called the radius. And from the circle to the radius to the circle go both sides is the diameter. The relationship is that d equals 2r. If you go around it, you cover the circumference 2 pi r. and the area is pi r squared. In this question, we need the area, but I'm giving you all the formulas just to remind you. So A is pi r squared. The radius is increasing at the rate of 3/2 feet per second. That means dr dt is 3/2 feet per second. What are we looking for? The rate at which the area, the A dt, is changing. At what point? When r is 4 feet. So this entire question, word problem, application problem is translated into symbolic mathematical symbols in this format. So all you have to do, differentiate this. So A is pi r squared, and the A dt is pi. Pi is just a coefficient, is a number. Now you want to differentiate r squared to r dr dt, or 2 pi r dr dt. Two pi, replace the r with 4 feet, dr dt with 3/2 feet per second. And you get 12 pi units of the area over units of time, square feet per second. So 12 pi. This is exact answer. Roughly 37.6991 square feet per second. This depends on how many decimals they ask you. Okay. Find dy dt for the equation 4x plus 3y to the power of 4 equals x squared, where dx dt is 10, x is 4, y equals -2. The moment you see dy dt, it is telling you the independent variable is t, which means the derivative of x is no longer 1, is dx dt. You see that? So we are going to differentiate this term by term. The first one, 4x, gives us 4 dx dt. Then 3y to the power of 4. The derivative of the extended power rule, g of x to the power of n is n, g of x to the power of n minus 1, g prime of x. The derivative of y to the power of n is n, y to the power of n minus 1, y prime, or n, y to the power of n minus 1, dy dx. In this case would be 12 y cubed. Instead of dy dx, we're going to write dy dt, because we know t is the independent variable. So 12 y cubed dy dt equals x squared 2x dx dt. And we're done with calculus. We just plug in. There are two ways to solve this. One is to plug in. One is to solve for dy dt and plug in afterwards. I'm going to do both ways for practice. So first, it's easy, just plug in 4 times dx dt is 10 plus 12 times y -2 cubed, dy dt is missing, 2 times x is 4, dx dt is 10. So plug in. That's one way to do it. 2 times 4 times 10, this is 80. 4 times 10 is 40. This one, minus 8 times 12 is minus 96. We move the 40, subtract it from 80. We get negative 96, dy dt is 40. Divide both sides by the coefficient of dy dt. So you get 40 over minus 96. And you simplify, they are both divisible by 8. Dy dt becomes negative 5 over 12. The second method is to solve for dy dt, which means this moves to the right and becomes negative. And you're going to divide both sides by 12y cubed and divide by that. Also, on the right side, we can take the 2 out and dx dt out. So 2 dx dt, this gives you x, this gives you minus 2. And 2 goes away, this changes to 6. And we have dx, dy dt is dx dt over times x minus 2 over 6y cubed. That's what we get. Now, at this point, everybody, if you just plug in right here, plug in the values, you get exactly the same thing as we did here. Okay. You don't have to do both ways, obviously. Find dx dt in example 3 for the equation 3x plus y e to the power of x equals 20, where dy dt is negative 8, x is 0, y is negative 1. So we are going to differentiate term by term, starting with 3x. You get 3 dx dt. And then to differentiate this, we notice it's the product of y and e to the power of x. We put a raised dot in between. F times g, and we're going to use the product rule on that. So f prime is dy dt. Remember, t is the independent variable. Dy dt times e to the power of x. Now, what is the derivative of e to the power of x? It would be just e to the power of x if the independent variable was x, but the independent variable is t. So it's e to the power of x dx dt times y. That would be the g prime f. So one more time, e to the power of x dx dt times y. The number results in 0 when you differentiate any number. And this is the end of calculus. Just plug in. We're going to do this again 2 ways for practice. First, I'm going to plug in. That means dx dt is missing. Dy dt is replaced with negative 8. E to the power of x is replaced with 0 here and here. Dx dt is missing. Y is replaced with negative 1. When we do that, first, notice that e to the power of 0 is 1. So let me just replace that. So this is 1. And so if that is the case, this is 3 dx dt, this is minus 8, and this is minus dx dt. These two combine into 2 dx dt minus 8 moves, becomes positive 8, and 8 over 2 equals 4, because you divide right here by 2. And we're done. Now, the second method is to solve for dx dt, which means we're going to keep this, we're going to keep this. And then move this to the right and make it negative. On the left side, clearly dx dt is in common, so it gives us 3 plus y e to the power of x. when we factor the dx dt out and divide the right side by the parentheses, that gives you dx dt. And obviously, if you plug in, you will get the same answer, 4, as we did already. All right. We want to find example for dy dt for the equation 5x plus y to the power 4 minus x equals 6, where dx dt is 3, x is 2, y equals -9. And again, you can do it both ways, but I'm going to do one way now. We have enough practice, and you're more than welcome to try it with the second method. I'm going to just differentiate with respect to t, starting with the extended power rule. 4 times the parentheses cubed. So I'm looking at the extended power rule. The derivative of g of x to the power of n is n, g of x to the power of n minus 1. It happened to be g of t. G prime of x. Now, the derivative of the inside, 5x is 5 dx dt, and y is dy dt. So that's the first piece. Now, minus x minus dx dt, and any number results in 0 when you differentiate. And again, we're done with calculus. We plug in everybody, which means 4 parentheses 5 times x, which is 2, plus y, which is -9, quantity q, 5 times dx dt, which is 3, plus dy dt, which is missing, minus 3 equals 0. So we plug in. What do we plug in? What's given? What do we find? What's missing? Dy dt. All right, so this is 10 minus 9 is 1, and 1 cubed is 1, so it has no bearing, and this is 15. So we get 4 times, this one is 1, we don't even have to write it, parentheses 15 plus dy dt minus 3. We are going to distribute the 4. The product is 60 plus 4 dy dt minus 3 equals 0. 60 and -3, they add up to 57. And you move it, you make it -57 on the right, and finally divide by 4. Dy dt is -57 over 4 as the final answer. Falling sand is forming a cone-shaped pie. The volume of the cone is increasing at a rate of 54 pi cubic inches per minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches. Again, an application problem. You need to read it a couple of times. Starting from the top, falling sand is forming a cone shaped. What shape is that? This is the cone. This is the radius of the base. This is the height. And we want to relate the volume to the height and radius. We should know the formula. The volume is 1/3 pi r squared h. We should know this. So the volume is 1/3 pi r squared h. Now we're going to continue reading. The volume of the cone is increasing at the rate of 54 pi cubic inches per minute. So that means dV dt rate. So dV dt is 54 pi cubic inches per minute. The height twice the radius. H is 2r. H is equal to 2r. Find the rate at which the radius changes. Find dr dt. At what point? When r is equal to 6 inches. So this entire question has been symbolically translated. The volume is 1/3 pi r squared h. dV dt is 54 pi cubic inches per minute. H is 2r, dr dt is what we want to find at a specific point when r is equal to 6 inches. And so having said that, we want to differentiate this. It's important to understand we have the variable r, the variable h, and if you want to differentiate it the way it is, you need the product rule. However, h is 2r, and you can replace it. Now, they are asking for dr dt, so you're going to replace the h. If by any chance they're asking for dh dt, you can replace the r. R is h over 2, okay? Remember when h is 2r. So first and foremost, replace the h with 2r. So 1/3, the volume is 1/3 power squared times h, which is replaced by 2r, and therefore it's 2/3 pi r cubed. Now we are ready to differentiate. Now we are ready to look at dV dt, and again, it's important to understand this part, everybody. It's just a number. So dV dt is 2/3 pi. It's a coefficient, it's a multiplier. And now all you have to do, differentiate r cubed with respect to t, and that's an easy differentiation, 3r squared dr dt. Two pi r squared dr dt. You can either solve for dr dt or just plug in. That means replace this one with 54 pi and the r with 6. Six squared is 36 times 2 is 72. So the right side is 72 pi dr dt. Divide both sides by 72 pi. And these two numbers are divisible by 18, 3/4 of an inch per minute. Units of the radius over the units of time. Or if you put here 54 pi cubic inches per minute, and this r, you put it 6 inches and then square it, it works out in the same manner. In other words, what we do to numbers, we do to units. A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. We have to draw the setting, define our variables. Can't be done otherwise. We must. So here's the building or the wall. Here's the ladder. It slips away at the rate of 2 feet per minute, the base. So we call the base x. Therefore, the rate would be dx dt is 2 feet per minute. As it moves this way, it creates a shape like this, a right triangle. This is X, this is Y. Those are the legs, and this is the hypotenuse fixed at C equals 20 feet. That's the ladder. As this comes down, creates the speed dy dt, because we call this side y, dy, the height is h or y or whatever you want to name it, dy dt. And C is fixed, 20 feet. So we are ready to write the given symbolically. Dx dt is 2 feet per minute. This is a right triangle, and therefore we should know a squared plus b squared equals c squared. It's Pythagorean theorem. So x squared plus y squared is 20 squared. We want dy dt when the base x is 12 feet. This is writing the question symbolically. And this is relating the two quantities, x and y, to solve the problem. So x squared plus y squared equals 20 squared. Of course, 20 squared is 400. We're going to differentiate this, 2x dx dt plus 2y dy dt equals any number, results in 0 when you differentiate. So we want to find dy dt when x is 12. So we have the x, we have the dx dt, but what is y when x is 12? We must plug in and calculate. So when x is 12, we get 12 squared plus y squared equals 20 squared. 12 squared is 144. 20 squared is 400. Subtract. You get 256. You take a square root, y becomes 16 feet. Now we can plug in and we have everything except dy dt. So when we plug in, 2 times 12 times 2 is 48. 2 times 16 is 32. We get 48 plus 32 dy dt is 0. Move the 48, make it negative. Divide both sides by 32. So dy dt is negative 48 over 32. Both numbers are divisible by 16. This becomes minus 3. This becomes 2. So dy dt is negative 3 halves feet per minute, units of y over units of time. And again, bear in mind, x is increasing. It's getting larger. Dx dt must be positive. Y is decreasing. It's getting smaller. Dy dt must be negative. And it is. Now, if we look at the same situation, the same question, notice not only y is changing and therefore dy dt is changing, this angle as well as this angle are both changing. Okay, so let's look at the same situation. A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute. Find the rate of change of the angle between the ladder and the ground when the base is 12 feet from the building. In other words, same situation. Here's the building or the wall. Here's the ladder. It's going to move this way. And as it moves this way, as it creates a speed or rate of 2 feet per minute. And it creates the shape, a right triangle. And this moves this way, the height moves down. Okay. This side is fixed, c equals 20 feet. And this is the angle of interest. Find the rate of the change of the angle between what? The ladder and the ground, this one. So theta, and therefore we are asking for what? D theta dt. So you want to be very careful with what is asked. And of course, we're going to write exactly what we wrote in the previous page. In other words, we're going to write dx dt is 2 feet per minute, x squared plus y squared is 20 squared, but this time we want d theta dt when the base or x is 12 feet. So that's how we write it. So in related rates, you relate two quantities. What quantities? The one that is known, dx dt is known. By the way, one might say dy dt is known also, but dy dt is known from the previous page when we calculated. But you use the one that is given to you. So dx dt is known. So you want to relate the x to theta because you want d theta dt. So x and theta, that's how you want to do that. And as you know, sine of theta is the opposite over the hypotenuse, and cosine theta is the adjacent over the hypotenuse. Now, the sine theta is y over 20. Cosine theta is x over 20. So we are going to use the cosine theta because x is known, everybody. Okay, you can use any of it. And you can say, okay, I know the y and the dy dt because we've calculated. But stick with what you have been given because we may have made a mistake with our calculations. So having said that, we're gonna use the cosine, everybody. Cosine is x over 20. And it's important to understand that the derivative of cosine is very simple. Negative sine theta, and then d theta times d theta dt. Okay. Left, that's the left side and it's done. The right side, I'm going to rewrite this as 1 over 20 times x. So 1 over 20 times x. X gives you dx dt. The reason I'm writing it in this fashion because I want to make sure it's clear that 1 over 20 is the multiplier, is the coefficient, and it doesn't do much. Now I'm going to say minus sine theta is y over 20. Okay. D theta dt, 1 over 20 dx dt. So I'm going to replace the sign with y over 20. And again, we did this in the previous page. Y is missing. We said x squared plus y squared is 20 squared, and we showed that y is 16 feet. So I'm going to use that, and I'm going to replace the y with 16 and dx dt with 2. Now, notice you have a couple of fractions, and we have the denominator 20. You can just drop the denominators because they are identical, which means you really have, just show this, you have minus 16 d theta dt equals 2. That's the meaning of it, everybody. And so we're going to divide by negative 16. And the result would be negative 1 over 8. Negative 1 over 8, what is the, what are the units? Units of the numerator over units of the denominator. Units of theta is always radians in calculus, and of course we know the time is in minutes. So negative 1 over 8 radians per minute. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius changing? Well, again, reminding everyone, here's a sphere. The volume is 4/3 pi r cubed because we are relating the volume to the radius. So that's a formula we should know. So the volume is 4/3 pi r cubed. Let's reread the question. So it's deflating, losing 8 cubic centimeters of air per minute. So right here, it tells you it's a dV dt, it's the rate, is minus, and that's the point, deflating or losing, minus 8 cubic centimeters per minute. And at the moment when the radius is 20, when r is 20, we want to know what's dr dt, how fast is the radius changing. So we're going to write the formula for the volume, 4/3 power cube. Given dv dt is negative 8 cubic centimeters per minute, missing dr dt at the moment that the radius is 20 centimeters. So we're going to differentiate this, and we have done it already. So I'm going to go over that one more time. dv dt is 4/3 pi times now r cubed. So again, 4/3 pi, 4/3 pi is the coefficient, the multiplier. It's just a number. So r cubed, 3r squared dr dt. And it simplifies to 4 pi r squared dr dt. We can solve for dr dt, or we just plug in, meaning dv dt will be replaced with negative 8 and r with 20. 20 squared is 400, times 4 is 1600. So we have 1600 pi dr dt. We're going to divide by 1600 pi. Minus 8 and 16 cancel each other. This becomes minus 1. This becomes 2. So it becomes precisely negative 1 over 200 pi units of the radius, centimeters, per units of time, minutes. Therefore, precisely negative 1 over 200 pi centimeters per minute. Roughly, putting it into calculator with a bunch of decimals, negative 0.001592 centimeters per minute. And it reads, the radius is decreasing at a rate of 1 over 200 pi centimeters per minute. Why is it decreasing? Because it's negative. And the moment you mention decreasing, you don't have to write negative 1 over 200 pi. In fact, it makes it wrong if you do so. So the radius is decreasing at the rate of 1 over 200 pi centimeters per minute. Again, precisely, everybody.